Good.
Okay, great. So we're happy to have Josh Foster from MIT, and he's going to tell us about searching for new physics with gamma-ray telescopes.
Okay, well, yeah, thank you everybody for being here and sneaking me into the seminar schedule. So, good. My talk is about searching for new physics with gamma-ray telescopes, like Shruti said. So let's just dive in and start with some big picture remarks. So I am a dark matter phenomenologist. I'm really interested in going out and looking for dark sectors and dark matter and physics that has as of yet eluded us just because it's not emitting light very brightly. And I think about this a lot in the context of astrophysics. And maybe I can just motivate why we should think about astrophysics and cosmology when we're looking for new physics, especially dark matter. When I was starting graduate school, somebody basically pitched working at the sort of interface of searching for new physics with Cosmo-Astro type searches by saying the data sets are so big and so rich that if you open them up and look at them in a careful way, you're going to find an anomaly. And maybe that anomaly is just boring standard model physics, but maybe it's not. Maybe it's something new and we have a chance to make a discovery. And that's certainly true in the case of dark matter. So maybe one sort of template observation we can make is going and looking at galaxy rotation curves. So essentially, as a function of radius from the galactic center, how fast are stars moving? And you can compare those measurements with predictions of how fast could those stars be moving in order to not escape from the galaxy. In order to make that prediction, you need to know how much matter is living in those galaxies. And if we go out and just count up all of the matter in baryons, the matter that's essentially in stars and is shining back at us, we can make a prediction for that maximum velocity. And that maximum velocity is going to turn out to be much smaller than the velocity that we actually observe stars moving with. So that's a little bit funny, and maybe it evidences that we didn't manage to successfully count up all of the matter in that galaxy, and we can just hypothesize that there's some extra matter, some dark matter, that increases the total amount of matter and would reconcile our theoretical predictions for what the maximum velocity could be with the velocities that we actually go out and observe. And this might seem sort of kludgy. We have one anomaly. We introduced a whole lot of new matter to go solve it. But it turns out that other observations, so for example, looking at the bullet cluster, large-scale structure, which traces the matter distribution of our universe, and CMB surveys, all of these support that there's actually some missing matter that we wouldn't have accounted for if we said the only thing out there was baryons, the sort of thing that makes up you and me and stars. So putting that all together, the matter that we know and understand theoretically, at least we think, is living in this 16% of the total matter fraction, this standard model that is very, very well tested and successful. And by comparison, 84% of the matter of our universe seems to be dark matter. So that's all we know about it. It's dark, it's not giving off much light. All of these probes are purely gravitational. They just say it's there and it weighs something. It doesn't tell us what its particle physics identity is or what its specific interactions and cosmological history might be. Okay, so when we want to think about searching for dark matter, because we don't have any idea, like first principle from measurements, what its particle physics properties are, other than that if it has interactions, those interactions are weak, we have to start thinking in the context of what is a good model for dark matter? Given that model, what are the channels through which we do actually have a chance to go observe it? And when we perform those searches, are we actually seeing anything? So this is sort of a paradigm you might have heard about before in dark matter physics. So really, it's summarizing three strategies. Let's see, make it, break it, or shake it. So the idea being, if I have some dark matter, I can think about that dark matter, for, let's say, breaking the dark matter. So I have dark matter scattering going into two standard model particles. I can turn this diagram so I can make dark matter scatter off of a standard model particle. I'm shaking the standard model particle as I go from dark matter standard model to dark matter standard model. Maybe I can see the effects of that shake. And then finally, the make, the break it searches. These are our astrophysical searches, looking for dark matter annihilating on the sky and producing high energy photons that would reach us here on Earth. The shake it, this is like your liquid xenon searches, so waiting for some heavy particle to come interact with some otherwise inert gas. And then finally, the make it being standard model scattering to produce dark matter particles. This is the type of search that you might think of at the LHC. Okay, so it turns out that, well, this is a paradigm of dark matter searches that we've thought about for a long time. And this actually is really coming from this search for new physics, new particles at the weak scale. The idea being weakly interacting massive particles might be a good dark matter candidate, and really we could probe them through all three of these mechanisms. Now it turns out another class of models you might think about are neutrinos. So what if there are extra neutrino species in the spectrum? Then actually maybe we can go and we can look for those also in this sort of similar make it, break it, or shake it type paradigm. So for example, one thing I've thought about is using X-ray searches to look for decaying stereo neutrinos, which is actually pretty similar to using gamma ray searches to look for decaying weak scale, or rather annihilating weak scale particles. So just for completeness, I'm highlighting this whole section here, and I'm just labeling it gravitational probes. So these are really, with some exceptions, but these are generally dark matter models that are going to produce not so distinct sort of cosmological, or rather indirect, direct, or collider observables, but we would see by modified gravitational dynamics of celestial bodies. So these, I think, we can all sort of safely categorize as gravitational observables. And finally, I wanted to highlight this, this blue section, and I'm just putting a question mark here. So this blue section is identifying light bosons. So really what I mean by this is I mean axions, axion-like particles, and maybe dark photons as well. And there are lots and lots of ideas for how to go look for previously undetected light bosons. And some of those detection strategies do map into this make it, break it, or shake it paradigm. But actually, some of them don't. This is sort of an emerging field. The range of masses that we think about when we think about light bosons is many, many orders of magnitude. And it leads to sort of a diverse phenomenology and a range of new detection strategies. So this is just sort of setting the course for what this talk is going to be looking at and providing a little context. So really what's going to be of interest here is what's highlighted in green, these searches for weak scale particles, as well as, if we have time to get to it, what's highlighted in blue, some of these searches for new light bosons. And since I'm a sort of astro-cosmo type person, that's the lens that I like to take or to use when I'm looking for new particles, I wanted to show this plot, just summarizing a little bit of what's the landscape of the telescopes and observatories that are available to us when we want to use looking for high energy photons as a probe of new physics and of dark matter. I'm also, I'm lucky enough to be giving this talk sort of immediately after snowmass, which means there are a lot of nice graphics summarizing the state of the field floating around that I can quickly adopt. So this is from a Theory Frontier white paper called Astrophysical and Cosmological Probes of Dark Matter. And what it's showing you in orange are existing telescopes, telescopes that have been collecting data now for some time. And these hatched gray regions, these are new telescopes that we expect to have in the future that will give us new sensitivity looking at our high energy universe. So what this is showing you is it's showing you this plotted with energy of the photons that it's sensitive to as a function on the x-axis. And here what I'm showing you is the effective area of the telescope times the exposure time projected over the observatory's mission. So this is basically, the x-axis is telling you what energy photons you're sensitive to, and really exposure times effective area is telling you how many total photons do you actually expect to see using one of these instruments. I should say also that, like, you know, in many cases you see that there are some new instruments that are just poking above the orange, and this doesn't mean you should be depressed about these new instruments. Effective area times exposure is just one sort of way of comparing these instruments to one another. So let me just highlight a few specific instances. So right here, living sort of from MEV all the way up to TeV energies is Fermi. So Fermi's been a long-running gamma ray telescope that's going to be relevant for what's coming later in this talk. And you can see here that Fermi is actually beating some of these future MEV telescopes like e-ASTROGAM and AMEGO. at least beating in the plane of effective area times exposure. But AMEGO and e-ASTROGAM will have much better, for example, spectral resolution, angular resolution in terms of discerning what they're actually looking at on the sky. And these will lead to, these improved features will lead to better sensitivity of, among other things, dark matter physics. So just to sort of organize, all of these orange regions, these are basically long-running experiments where we have a chance to do sort of mature science. They've taken a lot of data. We should figure out what is everything that we can wring out of them in terms of our searches for new physics. Whereas these gray regions, like AMEGO or e-ASTROGAM, these are new searches, new telescopes that will come online, and we should think about what is the new science that we can actually do with them should they be built. So that's the landscape. All right. So now I want to pause and give just something of an outline for this talk. So we've gotten an introduction to dark matter in the search paradigm. We've seen We've seen that there's a sort of a complicated model landscape, but at the very least, there's a quick, pithy way of saying the detection strategies: make it, break it, or shake it. And we've seen a little bit about what we can do, at least on the break it frontier, in terms of looking for new dark matter from its annihilation or decay on the sky. So now that we've done that, I want to pivot into the second part of this talk, which is going to be about searching for higgsino dark matter. What I'm going to do here is generally motivate looking for dark matter with Fermi and telling you what is the status of searches for annihilating dark matter, and then how we can maybe do a little bit better in the case of the searches for the higgsino. Okay. Great. So I am copying this picture again. This make it, break it, or shake it, but really we can think of it again as in the early universe now. I don't want to think about this particle on its own, but I'm going to say there's some dark matter. It's living inside the standard model bath at very high temperatures at very early times, in which time there's momentum exchange, there's dark matter production, there's standard model production. All of these processes are initially in equilibrium, or at least I'm going to assume such. Now, as I reduce the temperature, these processes are going to freeze out. So really what you want to study, and you want to ask is, as a function of temperature, what is the rate, for example, for a dark matter scattering into standard model? If that rate is very small compared to Hubble, then that process is frozen out. And we would say that there are no more dark matter annihilations happening, at least not at a rate relevant on cosmological scales. So the quick pattern is we have an initial equilibrium. At first, the temperature drops. When the temperature drops and the standard model particles are no longer carrying enough energy to actually produce dark matter through their scatterings, all we have happening, we no longer have standard model to dark matter, but we can have dark matter to standard model. Eventually the universe expands, the rate drops, and that freezes out as well. And now we have no number-changing processes. We have no processes that are either making or destroying dark matter, and the number density that we have is the number density that we have. So we can ask, what does this look like sort of as a function of, let's say, the dark matter mass and the dark matter interaction cross-section? And really what we want to know is, for some hypothetical particle, how much abundance do we realize in the late universe? So what I'm showing you here is for a few different, this is a plot I've taken from some old paper now, but I'm thinking about a few different dark matter masses, sort of on the order of a GeV or a TeV, and I can say, all right, well, let's assume that dark matter has an interaction strength that's roughly consistent with the cross sections that we see in QCD, strong interactions. Now, in that case, the annihilation, which is really being parameterized by this sigma v, the velocity average annihilation cross-section, is quite efficient. And we would find that we don't get very much late-time abundance at all of these sort of strongly interacting massive particles. Now, if we step the interaction strength down from sort of typical strong force strengths to typical electromagnetic strengths, then we have less efficient annihilation, but still not very much dark matter left in the universe. And what's very, very exciting, actually, is we were already assuming GeV to TeV scales, which is roughly the masses of particles that we think of associated with the weak force. And if we assume that these new particles have an annihilation cross-section roughly set by the the weak scale interaction strength, then we find that really almost independent of the dark matter mass, the late time abundance is in very, very good agreement with the abundance of dark matter that we go and observe in our universe. So this seemed quite compelling, that maybe indeed the dark matter is weakly interacting massive particles, and we should be looking for that. This sometimes gets referred to as the WIMP miracle. Okay, so when we think about going and looking for weakly interacting massive particles, what we want to do is we want to say if two particles find each other, then they annihilate and they produce photons. So I can think of this sort of, what is the photon flux associated with annihilating dark matter? So we're calling that, two phi's here, that's unfortunate. One phi is photon flux, this phi really should be like solid angle. This would be better as an omega than a phi. Sorry about that, everybody. Yes?
So on that last slide, this graph that you showed, on the y-axis, what you're looking for is that it should end up at...
Should end up right here at Lambda-Cedium. Yeah.
Okay, and if you vary the initial energies for the green, for the strong and electromagnetic couplings, you can't get that omega CDM to be 0.3 today. So the variation you show is only for the weak interaction, right?
The variation? No. I mean, this is a very hand-wavy plot, right? Like I'm just assuming there's some annihilation cross section, and I'm just plugging in values, and this. So I'm varying it between not explicitly saying like, oh, this is actually a particle that is interacting through like electromagnetism or through QC or whatever. I'm just taking illustrative values of what the cross section would be for that type of interaction. So I'm making, sigma, this is the biggest, and this is the smallest in this sort of tower that I'm looking at. I mean, it is nice that sigma v for the weak scale, roughly, is giving us the right answer, because, if it was living down here, well, maybe I wouldn't find things as compelling, because then I would need something that's interacting more weakly than the weak force, and I lose some of my motivation to tie together this GeV, TeV scale with cross sections and so on. Does that make sense?
Yeah, thanks.
Cool. All right, so as I was saying, what we want to do is we want to look for dark matter annihilations on the sky. So I want to think about the photon flux. So how many photons am I seeing as a function of energy and location on the sky? So I can break this up into two things. I can break this up into some particle physics factors and some astrophysics factors. So the particle physics factors, these are just saying, I don't care where the dark matter annihilation happens. As long as it happens, I have sort of some set of invariant things occurring, which is I have the rate for annihilation is going to be determined by this overall sigma v, this velocity average cross-section. But once I have an annihilation, the spectrum of photons that I see is going to be universal. It's going to be parameterized by this dn dE. So these are our particle physics factors. And then in terms of where to actually look, this is going to come from the astrophysics. Because we need two particles to see each other, to find each other in order for annihilation to happen, the rate for annihilation is essentially going to go like density squared. Excuse me. And what I have to do is I have to integrate that dark matter density squared along the line of sight, which is just saying everything along the line of sight I have a chance of seeing annihilation at, not just one location in the 3D space. So sort of two places that you might think to go and look for dark matter if you're taking this approach to look for annihilations are first the galactic center. We might like to look at the galactic center because the dark matter, there's a lot of dark matter in the Milky Way. At the galactic center, the density profile should be peaking, which means you should get even larger dark matter densities dark matter annihilation rates, since you're dependent on an overall rho squared. On the other hand, there's a lot of stuff. There's a lot of baryons. There's a lot of hot gas at the galactic center, which means although you might expect there to be a bright dark matter signal, the backgrounds are also quite intense. And you have a chance to make an interesting discovery if you can accurately model the backgrounds. On the other hand, that can be a pretty big challenge. So a sort of more modest choice of where to go look are at dwarf galaxies. So dwarf galaxies, like let's say Segway 1, for example, Dwarf galaxies are so small that although they're dense in dark matter, they weren't actually, they don't have deep enough gravitational potentials to keep baryons in them. Essentially, a galaxy might start to form inside a dwarf galaxy and then feedback as stars form and energetic particles are injected, causes them the baryons to dissipate and escape the dwarf galaxy. What this means is that late times, these are like particularly clean in terms of low backgrounds, and although we don't expect to see as bright signals, it's a complementary probe to the galactic center. In this work, I'm going to focus on the galactic center, though.
Sorry for this question. This row kappa, this is energy density or number density?
Oh, good. This is energy density, but I have this m chi living here to make it number density.
Okay.
Yeah. Sorry, I snuck m chi over here into the particle physics factors.
I believe that should be 1 ds, right? That ds.
Oh,
ds.
oh, I see. I have multiple typos in this expression. Yeah, I don't know what that ds is doing there. That's bad. Yeah.
So what's the scale dimension s? The dimension is what's s? ds.
What's ds? I mean, so this is just integrated along the line of sight. So you're integrating. I mean, the.
What's the dimension of the ds?
So what dimension?
Yeah, scale dimension.
Kiloparsecs, right? I care about going from me here at the Earth's location to the galactic center, which is about 8 kiloparsecs.
Okay.
Yeah. Yeah. Okay. Excellent. I got some fixes to make on this this expression. ds is confusing. Thank you for pointing that out. Okay, so this plot is just here to really help you navigate, like, what is the current status of searches for annihilating dark matter? And, okay, so let's start with these lines. These lines are some different results using 6 years of Fermi data, so data from this Fermi Large Area Telescope that goes from MeV energies all the way up to TeV energies. And so, let's see, in red, these are the limits that you can set on an annihilation cross-section as a function of mass of the dark matter particle that's coming from looking at the Milky Way galactic center. On the other hand, let's see, here in blue, these are the limits that you can set on annihilations from looking at dwarf galaxies. So taken on their own, I mean, it's okay. It certainly tells us we have more work to be doing, since at least for this annihilation channel where you have dark matter goes to BB bar. Even your best constraints are only ruling out dark matter particles at a mass below 100 GeV, whereas really we'd like to be able to extend these constraints all the way up to 10 TeV, let's say. And again, there's another sort of associated challenge in that you might ask, what are these bubbles? What are these circles? So these circles are sort of 1 sigma containment regions for the galactic center excess. So one thing that's it's very compelling, but it's also very uncertain as to what's actually going on, is searches where you look at the very inner galactic center and you look for some excess of photons that's consistent with the dark matter interpretation. They do actually pop up some excess photons. So if you choose to interpret that excess photon spectrum as dark matter, you might say to yourself, oh, I believe this looks like evidence for 50 GeV dark matter with a cross-section around actually the one that is preferred for the correct relic abundance. That's very exciting. On the other hand, this interpretation is nominally ruled out by the searches for dark matter annihilation in dwarf galaxies. So, well, there's maybe some exciting anomaly. There's also certainly work to be done in terms of reconciling the probes that we're able to make. Cool. Yes, this is just a summary plot here saying, okay, this essentially is the spectrum associated with the galactic center excess that you see when you would go out and do one of these searches. And what you should compare it to is in this dashed blue, this is like the best fit dark matter annihilation spectrum. So it's sort of, it's a little bit up in the air. I mean, blue does not seem to be an incredible fit to the extracted spectrum. So maybe that makes you feel like there's really some systematic mismodeling issues going on. You shouldn't take this too seriously. On the other hand, the excess, which is extracted in a purely data-driven way, does seem to be somewhat robust, and at least at low energies, appearing at very high significance. So there's definitely something to think about here.
Sorry, so I'm not familiar with this. So what's being plotted here is the excess.
Yes, so
This is the excess after you claim you subtracted.
did all the backgrounds off, yep. Yeah.
And so it's like a million sigma.
It is like a million sigma, especially...
Really, really, right? Yeah.
Yes, yes.
Okay.
And especially if I tell you, well, I guess it's also in this
So
plot.
this red broken power law, which does fit the data, is just some formula, it's not a model.
Yep, that's just, yeah, purely saying what if there's a broken power law, and that's what the excess is. There's also no spatial information being put into these analyses at the level of like just fitting this spectrum. It's just purely saying like I have these residuals. Oh, it does sort of look like a broken power law. On the other hand, many things in astrophysics look like broken power laws. So maybe you're not like super impressed by this or super depressed by this.
No,
It's just
yeah.
yeah. No. It's an effect that is definitely. I mean, the excess is definitely there at the level of the statistics. This is really a question of systematics, and are you really modeling all of the things that are happening in the intergalactic center, which seems like a tough ask to me. Cool. So my personal perspective on this is that, well, one, we're already getting interesting sensitivity to dark matter from searches like Fermi. But also that we do need to think about how to do careful Fermi analyses that have real sensitivity and real detection power, rather than some of like this search for that found the galactic center excess. This is awesome, but it also hasn't really convinced anybody, right? Like so, there's sort of there's science work to be done in terms of like how do we do the best analyses possible, but there's also almost sociological work. How do we choose the analyses that like we really believe we can convince ourselves are doing what they're supposed to be doing?
Just to get some idea, I know it's a really complicated question, but if you go back to that galactic center excess plot,
This one.
like what fraction of the total rate is the excess?
So the number is roughly 5 or 10% of the total
10%.
observed photons.
You
Yeah.
guys believe that they can model it to that accuracy?
Yeah.
Very, very lucky.
And this is really tricky because like the way these analyses are done, these aren't like purely spectral analyses. These are template-based analyses. So what you're doing is you have a map. So maybe you can see something like this, right? Here is a pixelated map of all the photons that are being observed. I think roughly above 3 GeV, zoomed in on the intergalactic center. And you're trying to fit not only the spectrum in each pixel, but the total normalization in each pixel from some assumed spatial model. So this becomes really hard, right? Because like, let's say there's a pixel that, or a set of pixels that just contains some like unmodeled hot gas. Like that, if that's unmodeled, then this is going to cause a systematic offset between your assumed model and the data that you're actually getting, and you very quickly become sensitive to unmodeled features that you didn't actually want to deal with, and you have a hard time, again, convincing people that everything that you did and said was realistic. Now this is I should also say my sort of perspective on it. Like different people will disagree, but I think it's important to think about like how you can actually do these analyses in a robust way, not just in the way that theoretically gives you the most statistical sensitivity. Okay. So when I'm thinking about like how can we do Fermi analyses that are sort of maximally informative for us now, I want to do like a few things. One, I want to look for dark matter candidates that haven't been ruled out by previous analyses, but also I want to not deal with low energy photons. I want to sort of avoid these questions of is the galactic center excess real, and can I really successfully model that at the level of the statistics? So what I want to think about a little bit instead is how can we improve the sensitivity of Fermi searches for heavy dark matter? Because at heavy dark matter, we're going to have support for photons at energies that are very high, let's say 100 GeV, which is still well within the Fermi range, but also outside the energy range at which the galactic center excess seems to be particularly bright. And in this context, I want to think about Hexino dark matter. So I don't want to spend time defining what Hexino dark matter is. Hexino dark matter is what's in your heart. But one of the reasons that Hexino dark matter has been an important benchmark scenario for dark matter searches is that if you look at this violet shaded region, this is the plane of dark matter mass to proton interaction cross section. And the point is, if I look at my neutrino floor, that's this dotted line, and I compare it to this violet region, which is the pure Hexino region of the parameter space, I find that almost all of my interesting range for Hexino dark matter is well below the neutrino floor, which means that really I don't expect to ever be able to see this with direct detection experiments like xenon anton or LZ or so on. So if we're going to look for Hexino dark matter, we need to look for it in the break it or make it way. The shake it direct detection is not going to work. And here I'm showing you essentially projected constraints that are coming from a search for Hexino dark matter, well, not a real search, a simulated search, that are using the Cherenkov telescope, which is a planned future experiment that will have sensitivity to dark matter between 100 GeV and maybe all the way up to 20 TeV. So this is an important future instrument. And in the future, well, really we expect our thermal Hexino dark matter to have a mass of about 1 TeV. And at least in this benchmark projection, CTA is telling us that the preferred mass is here, the preferred cross-section is right here, and their 1 sigma containment interval for their limits is this green band. So CTA is trying to tell me that they think they can get to this benchmark model given the time and given the assumption that this thing actually gets built and works. But I want to see what we can do to go look for Hexino dark matter right now.
Right, the solid line is the spectrum, but you have a spectrum with 2 sigma and 5 sigma. Can you?
Oh, good. I'm sorry. When it says full spectrum, what this is saying is that they're doing a search where they are projecting sensitivity from the entire annihilation spectrum, the whole DNDE. And I'll get into what is different about that.
Oh, I see. And the 5 sigma and 2 sigma they're different analyses of the same.
Yeah. So this is if I'm remembering correctly. So 2 sigma, if you have this solid red line, if you have dark matter living along this red line, then you expect to detect it with CTA at 2 sigma significance. Okay. And then this is at 5 sigma significance.
Okay,
yeah.
I got it. And then the prediction is the solid line.
The predicted, is the solid line, which is accounting for like Sommerfeld enhancement, which is why it's got these peaks.
Right.
Yeah.
Okay, thanks.
Yep. Okay, so but good, this is going to give me an opportunity to explain what does it mean to look for the full spectrum versus not the full spectrum. Not the full spectrum seems odd. So here I'm showing you, you can ignore this sort of Y scale here, but here I'm showing you what does the spectrum as a function of energy look like for Hexino annihilation, where we're getting contributions from processes that give us continua, like dark matter to ZZ. But we can also have, or dark matter to WW, but we can also have direct annihilation of dark matter to photons. So what we're seeing here is we get this line-like feature, which is associated with dark matter to gamma, along with this continuum feature, which is associated with the dark matter to gauge bosons, or heavy gauge bosons. So this is a good annihilation line target, and it's actually the one that's being searched for by the Hess collaboration. So here I'm showing you the sensitivity that Hess has from this sort of scatter plot compared to what the thermal relic cross-section for the line is, because Hess is only looking for the line. So we have a pretty basic question going into this work. Sorry, I'm just checking how I'm doing on time. Good. We had a pretty basic question going into this work, which is how does the Hess sensitivity compare to the Fermi sensitivity? And Hess and Fermi, these are 2 pretty different telescopes. So Fermi, it has, as I've been mentioning, has sensitivity to gamma rays at MeV to TeV scales. So like really it's like 30 MeV all the way up to maybe 2 TeV is the range of energy where Fermi is useful. Hess, on the other hand, Hess is cutting off at a lower energy of about 0.2 GeV. But it goes all the way up to 20 or 50 or however high you're willing to extend this plot. really what happens is you go to higher and higher energies, the effective area gets worse and worse. So your telescope is in principle sensitive, but less sensitive than is useful for any real search. So HESS is a ground-based telescope, and it's at these very high energies, and has a very large effective area. There are a lot of things that make HESS a great instrument, except HESS is fixed. HESS just points up, and it sees what's above it. And that means you can't say, like, my signal is going to be really bright at the galactic center, so I should just look at the galactic center for years. You have to say, like, oh, I got 10 minutes of galactic center transit today, and I'll just add that to my running data collection. So HESS has been operating for a few years now, and in total they only have 254 hours of exposure at the intergalactic center. Now, by comparison, Fermi is a space-based telescope, and it's hard to put big things in space. So Fermi, the effective area of Fermi is orders of magnitude below the effective area of HESS. On the other hand, Fermi's been up in the sky for 14 years, and it's a full sky instrument. So it has it sees about somewhere between 2.5 and 3 steradians on the sky, which means that we have actually years of effective observation time at the galactic center using Fermi. So, okay, so with HESS, better effective area, worse total exposure. And with Fermi, smaller effective area, larger total exposure. Thinking back actually about like that plot comparing telescopes that we saw before, this might make you initially think that HESS and Fermi have a chance at having comparable sensitivity. But there's another difference, which is that, again, HESS is just, because it's a high energy instrument, it's just looking for this sharp line-like feature. But there's a lot of photons living in this continuum that Fermi is going to have sensitivity to. So the hope here is that, and we're going to see this realized, that Fermi, by merit of both being a continuum instrument and also a very long-term exposure, will get us better sensitivity than HESS. Now, I should qualify, like, I have been warning about the dangers of going to low energies, just because you bring in this, this galactic center excess, this question about systematic mismodeling. So this spectrum does indeed have support below 10 GeV. For the purpose of this analysis, I'm going to cut off the energies of interest below 10 GeV. I don't want to mess with them, since I know there I'm going to get into ugly questions about, like, are there millisecond pulsars that are contributing to some excess. Now, it's possible I'm leaving some sensitivity on the table, but I'm doing it in such a way that is making my analysis a little bit more robust in terms of systematic modeling.
So what about this 5 degree mean?
What is 5 degree? Oh, good. I'm just showing you what the, so I had to take, this is a total intensity. So what I had to do to get that in total intensity, right, was choose some region over which I'm observing. So this is just averaged over the inner 5 degrees, whereas the dark matter signal is, of course, a little bit diffuse.
Okay.
Yeah. But 5 degrees, totally arbitrary.
Okay.
Other than a shift in normalization, it would have looked essentially the same for 1 degree or 100 degrees.
Okay.
Cool. So one thing I want to say, and I alluded to this earlier, is that typically these analyses are done by template fitting. So what I say is I define an energy bin, and then I look at the counts map in each energy bin, which might look something like this. So then what I would do is I would put together a bunch of different maps for the different types of emission that I expect to be contributing to the total number of observed counts in that energy bin. So here, let's say I've taken a dark map, I should say, I'm adopting both maybe, this slide from a really excellent talk given by Nick Rod. So the point here is that you have a total counts map, and you develop maps for different total contributions. So here we have a map coming from dark matter annihilation. This map actually looks a little bit funny, but it's because it's considering the contribution from extragalactic sources rather than the galactic center. If we were talking about the galactic center in this plot, there'd be a bright spot right here. But also what's being built in is this diffuse P7v6 diffuse model. So this is a model for diffuse gamma ray emission developed by the Fermi collaboration, along with other features like the Fermi bubbles, these spatially coherent bubbles that rise above and below the galactic plane, and then isotropic emission, which here actually doesn't look so isotropic, just because this is convolved with the Fermi observing pattern, and some areas in the sky have been observed for longer than others. Anyway, what you do is you associate a free normalization with each one of these templates, and then you go and fit it to the spatial map that you've observed in data. Then you perform this analysis in every energy bin, and then you translate the free normalization on the dark matter annihilation template into a parameter that's controlling essentially the annihilation cross-section. You join these together across bins, and then you get a final result for your best fit dark matter annihilation cross-section, along with, for example, 95% upper limits. But the idea here is that what we're doing is we're fitting a spatial map and then joining together different energy bins after we've done the spatial analysis. And I do want to say that there's a different way that we're going to do this, and I'm just spending time because I think it's a little bit unconventional in sort of this indirect detection analysis, is we are going to do something different. So rather than doing spatial fitting, then joining those spatial fitting results spectrally, we're going to go the other way around. What we're going to do is we're going to take our region of interest, which I'm defining as the inner 10 degrees centered on the galactic center, and I'm going to divide this into 10 1-degree wide annuli. Here you can see these little gray lines. These are defining the edges of the annuli. Now what I'm doing also is I'm masking out regions on the sky that are bright, that I don't have full confidence in my ability to model. So what I'm masking out here is 1 degree, plus or minus 1 degree in latitude, centered on the galactic plane. The reason I'm masking out that region is because I want to use diffuse maps that the Fermi collaboration has put together. Those diffuse maps are not calibrated within 1 degree of the galactic center. I just don't have the inputs necessary to accurately model this. So I'm going to remove this entire galactic plane. The other regions that I'm masking out here are point sources. So these are like particularly bright, for example, pulsars or nebula or other features that have been studied to some degree, and maybe we can say something about the total spectrum that's associated with them. But it's just simpler to mask these out than try to self-consistently model them in our analysis. So what we do is we sum up all of the pixels that are appearing within a single annulus, and we get that to define a spectrum, a count spectrum, observed within each annulus. So these are the data points with black dots. Here the error bars are very tiny, so you can actually see them. You can see they do indeed have error bars. We are eventually in the small counts limit. What we wanted.
So you don't expect the bubbles to be important for this?
The bubbles are actually, yeah. So, well, a few things. Maybe if you sort of squint, you could convince yourself that there's a bubble here. The bubbles, most of their support is at low energies. So because we've restricted to 10 GeV and higher, the bubbles are not like super visibly apparent here. But also, the bubbles are now built into the standard Fermi diffuse models.
Okay.
So that's living inside of our analysis.
Okay.
Yeah.
Okay, you haven't really talked about the background modeling.
Yep.
Yeah.
So good. So what I'm doing here is I start by summing up the counts observed in each annulus. So I'm getting my observed spectrum, these black dots. And now what I want to do is I want to try to model the observed spectrum with some combination of background models and the dark matter annihilation spectrum. So what I do is for example, I take the Fermi diffuse model, I convolve it with the instrumental response function, so I get the predicted number of background counts associated with any given diffuse model living in any particular ring. And that gives me something like what's shown in solid black. This is just the Fermi diffuse model opened up out of the box. And, well, first off, that's not terrible agreement, I think. It was comforting to see that the black line more or less passed through the data points, but we're going to do something more sophisticated in a
So
second.
that model was fit to data, obviously, right? But
That model was fit.
The claim is not this data. Is that the claim? And it just works for
Yes.
this data?
So that model is fit to the data, the same data, which may give you pause. But the things that are going into so you should be more concerned about this if we were doing a spatial template analysis. Because the way that this, this diffuse map is built up is the Fermi collaboration says, okay, there are a few different processes that contribute to astrophysical backgrounds, one of which is like inverse Compton scattering. Another one is Bremsstrahlung. And then, pions contribute a whole mess of photons. But these all have, like, essentially universal spectra. So what Fermi says is, well, I know what the spectrum should be from first principles. If I want a good diffuse map, what I need to do is I need to, like, fit the spatial variations in the intensity, not fit any spectral variations. Those are just what's given. So Fermi sets up a map that essentially has lots and lots of freely varying components. And then it fits the normalization of those components to the same data that's being used in the analysis. So that would be concerning if we were using a template-based fit, because in a template-based fit, what your concern would be, oh, there's a bright spot associated with dark matter annihilation. But Fermi would have just put that into a normalization in their map, and then our background model would already have contained the signal, and we wouldn't actually have any sensitivity. So for us, what's not so important is the total is the normalization or the spatial distribution. We just want to know, like, what the spatially average spectrum should be. And then which is what's in black. This is at least according to the Fermi predictions. But we're not using any spatial information outside of, other than that we averaged over some annulus. What we're going to do is we're going to fit a total normalization on that spectrum. And what's giving us discriminating power is that the spectrum of, for example, ICS processes is not going to be the same as the spectrum of dark matter annihilation. So that's sort of what's breaking our degeneracy. That's what we're using to gain sensitivity. So for example, we have the diffuse model. This dotted line, this is the contribution of point sources after accounting for that we've masked them, but point sources, because of the finite angular resolution of the instrument, they can leak out a little bit, so we can get some contributions from point sources. There could be isotropic emission that's associated just with the exposure map of the instrument. And then finally, in red, this is the signal that we expect to be associated with dark matter annihilation at a mass of, for a dark matter of a mass about 1 TeV. So you can see this spike associated with the line-like feature, and then this broader continuum. Okay, so what we do is we develop a Poisson likelihood. So what we're doing is we're just saying the total number of counts in each annulus is going to be described by the sum of the background model contributions and the signal model. All of those are going to have independent normalizations that I'm going to fit through maximum likelihood estimation to the data that I observe. And then I can join, for example, rings together. So here I'm just showing you very quickly. I mean, we have this. I have my Poisson probability mass function using mu here. Like, this is the what I expect the data to be given some model parameters, and theta, which are going to contain, for example, background normalizations and dark matter annihilation cross section. And then I perform this product over all the energy bins in a given annulus, and then all of the annuli that enter my analysis. And I have a likelihood for I have a likelihood for, as a function of the observed data and the parameters that I've assumed. And then it's really a matter of just sort of standard frequentist techniques to go and try to say, do I see an excess? Is that excess significant? And if I don't see an excess, what are the limits I can place on dark matter annihilation?
Sorry, what's the annuli?
The annuli are defined by these, they're bounded by these gray lines. And the idea here is that I want to, my signal has some particular spatial morphology to it, right?
Okay.
So I want to take advantage of that. So I want to say, like, oh, the signal should be peaked at the galactic center. So I want to break this up into annuli and say, well, in order for it to be consistent with the dark matter signal, it needs to be brighter here than it is here.
Okay.
Right? Otherwise, this would be inconsistent.
Okay.
Otherwise, it doesn't track the density, dark matter density profile, and it must be something else that's going on. Yeah. So this is a way of bringing back some of the spatial information without doing a full template analysis that uses exclusively the spatial map.
Okay, got it.
Okay. So one of the things that we need, so like we can go and we can perform this analysis, but it all depends ultimately on what the dark matter density profile of the Milky Way is. And so for a long time, and I still have the same ds squared in here, awesome. So for a long time, people just took like NFW profiles as an ansatz. And so NFW profile is just like a standard density profile that comes out of like dark matter only simulations of structure formation. And so we can certainly do that, and it's really useful to continue to present your results in terms of an assumed NFW profile, just because it makes it easy to standardize comparisons from analysis effort to analysis effort. But one of the exciting things about living in 2022 is that we're starting to hopefully get better at simulating what does realistic structure formation actually look like in galaxies where you have hot gas and baryonic feedback and a number of processes that we really couldn't have simulated before. So here I'm showing you, this is the gas profile of galaxies forming in the Fire 2 simulation suite. And so not only are we getting to see, for example, right here and here, Milky Way-like galaxies form. Like this is something that we observe even with now including gas and baryonic feedback in our simulations. But we can actually be so precise as to say, well, the Milky Way is pretty close to Andromeda. So maybe the most interesting galaxies for us to look at in dark matter simulations are pairs of galaxies that form relatively close to one another. And this is something that we see in simulation now. And it gives us a chance to like really, hopefully, better understand what the dark matter density profile of the Milky Way or Milky Way analogs should look like, and how we can use that to better interpret annihilation searches like we've been doing with Fermi. So yeah, this is the Romeo and Juliet galaxies that form the Fire 2 simulation. And here, what you can do is you can take the dark matter spatial distribution, velocity distribution, and so on, and you can construct this J-factor map, which is, again, this integrated rho squared along the line of sight. But here, this is being constructed from the Fire 2 simulation suite. We can get a J-factor map along the sky, and of course we can bin this into annuli just like we did our counts map, and we can get a look at the J-factors, so this integrated line of sight density squared, for 13 different Milky Way analogs that appear in the Fire 2 simulation. So in black is the standard NFW profile, and these colored lines, these are different profiles observed in the simulation. And one of the, I think, interesting things here that we're seeing in these simulations is for a long time there's been this question of what is the effect of including baryons actually do to your structure formation. In one camp, people were saying it should make you less dense in the inner galaxy. In another camp, where people saying it should make you more dense. And it turns out, well, at least the answer the Fire 2 collaboration gave us is that it can either make it more or less dense or more dense. They don't have one answer or another to give on this. And it's just illustrative of like some of the complexities that go into actually modeling this density profile. It is nice, though, to have a better understanding of the range of possibilities, especially because for this analysis, we can choose to interpret our results for any profile you like. So I can show you results for any one of these 13 profiles. So I'm really going to depend on showing you for the NFW profile. Okay, so flashing forward, showing you what the results look like. Okay, so the way to read this plot, on the x-axis, this is the mass of the Hexino, although again, like we were saying, really the best motivated mass is somewhere between 1 and 1.1 TeV, so that's the slightly shaded red region. In the solid red line, this is the relationship between the Hexino annihilation cross-section and mass. So this is really the target that you'd like your constraints to reach. This dashed black line is our best fit annihilation cross-section as a function of dark matter mass. And this solid black line is our 95% upper limit. So there's a few things to note here. If you compare our 95% upper limit with this dashed black line, which is the Hess upper limit, we're basically doing the same. We're beating Hess below 1.1 TeV. We're worse than Hess above 1.1 TeV. We have essentially the same sensitivity, the same constraining power for thermal Hexino dark matter. So why were our limits as weak as they are? We actually expected them to be stronger. Well, this yellow band is the 2 sigma containment interval on the best fit. And you can see based on our 2 sigma containment interval, we are observing an excess consistent with a dark matter annihilation at 2 sigma significance. So this is sort of compelling that maybe we are, even though we did our best to be conservative and restrict to energy ranges where we really trusted our modeling, and we're still seeing an excess that could be interpreted as dark matter. On the other hand, I have to look on the bright side of maybe this is a hint of a discovery, because had we not had a 2 sigma upward fluctuation, then these limits would have been, order 1 factors stronger. This is, of course, interpreted in the context of NFW annihilation profiles. If I ask what is the profile from the Fire 2 simulations that best fits the data, it turns out to be this Romulus galaxy, which is particularly dense at the within the intergalactic center, which leads to stronger overall limits on the cross-section, but again supports interpretation as an excess for this profile at about 2.5 sigma rather than about 2 for just NFW. So I think that there's like a few takeaways here. One, we've managed to design an analysis that uses this 14 years of Fermi data in a really effective way. It has better theoretical sensitivity than Hess, and indeed, if this is a real excess, which I have to hope it is, although I'm prepared to be disappointed, then maybe we would have only expected to see it with with Fermi, and maybe this is the first hints of discovery. I think it's maybe particularly compelling that for profiles like Romulus, our best fit annihilation cross-section is actually within statistical precision of what we really expect Higgsino dark matter to look like as observed on the sky.
So can I just make sure I'm understanding? So it looks like you've kind of done 2 things different from the Hess analysis. One is that you have, you've blanked out some things, right, which would give you less data, but then you've also gone out more in angle.
Yes,
right?
exactly. Yeah.
So you would somehow want to, so maybe naive question, but why shouldn't you just do both? I mean, if you didn't explicitly say you didn't believe Hess that they could model those regions, so wouldn't you want to do both, or do you think that? Can you just comment on that?
Yeah. So let me flip to this, which is going to half answer your question. So Hess has a very clean observable they're looking for, right? They're looking for a line. And so even though the intergalactic center is messy, I believe in your ability to detect a line, which is going to have relative width, that's set by the velocity dispersion. I believe in your ability to detect that line over some continuum, even if you're in a messy environment. So this is why I am totally okay and comfortable with Hess using just the inner degree of the galactic center.
Yeah, no, I think I just forgot that they're only looking at the very, very high energy stuff. And so that's why they can look at the line. So you're also going onto the whole spectrum. That's another thing.
Yeah. So there, I really just don't trust my ability to model the inner degree. But yeah, I was going to point to some work that I'm trying to finish up as a little bit of a follow-up to this. Is what happens if you use the inner degree? What does just the Fermi line sensitivity look like as compared to the Hess line sensitivity? So here I'm showing you, this is very preliminary, paper's not out yet, but constraints on annihilation or decay directly to photons using this exact same data set, but not masking the inner degree. And really what you can do here, so we should look at the annihilation constraints. In this solid gray line is what you get with Hess. So really above about 500 GeV, Hess does do better, even just looking at the inner degree, than Fermi does. I do certainly think it would be very well motivated for Hess to go and do an analysis that extends beyond the inner degree. I would do this myself, except Hess, unlike Fermi, does not have open data access. They've learned from a lot of really interesting Fermi science being done by not Fermi collaboration members, and so if you want to open up the Hess data and really do a search, you have to be a member of the Hess collaboration. But I think that it would be particularly well motivated to go and try to do the exact same Hess analysis, but yeah, out to 10 degrees as opposed to just out to 1. I expect you have 10 times, well.
Can you just make friends with somebody on Hess? I mean, that's what you have to do with the LHC.
Yes,
for
so
any of the interesting data, you have to make friends with somebody.
Yes. I think if I email them and I ask to join the collaboration, then they will allow me to open the data. But I think that is the threshold to...
I just need you get somebody interested on a
Yeah.
collaboration and you collaborate. Right?
Yep. Yeah, I think it's something worth doing. It's something that has been on my mind for like days now, as opposed to the week or so it would take me to muster up the effort to send that email. Yeah. Okay, so I'm at an hour, and I think I'm just going to skip over. No, I'm not going to drag you through a whole nother section. I'm going to give you the punchline. We should keep looking for new physics in gamma rays, and I have some new models for motivating KEV and MEV observables that you're free to ask me about, but I won't make you suffer longer. So really, thank you everybody for being here and for the excellent questions. It's been a fun talk to you.
We already had a few questions, but I'm guessing Josh is okay with taking more.
Yeah.
The analysis is model dependent, right? It depends on the Hexino model to
Yeah.
produce the
Yeah.
spectrum.
So
you have a different particle with different spectrum, you have to reduce.
we didn't, just because we felt like it was interesting enough to cast it in the context of the Hexino, but actually, because we're not doing a template analysis, because we're not trying to fit like hundreds of thousands of pixels all at once, like this analysis is very, very quick. It would be easy for us to just exchange, the Hexino DNDE with a different DNDE, and get your constraints for your favorite model.
I have no questions, but I'll ask them privately. I've already taken up enough of it.
All right.